So I'd like to welcome everybody to the fourth episode in our Spectrum Scale Expert Talks. My name's Simon Thompson. I'm the chair of the Spectrum Scale User Group in the UK. Today's talk is Update on Performance Enhancements in Spectrum Scale. So this year we're running a number of online talks. We've unfortunately been unable to run our in-person events this year, at events outside of kind of our control really. So we decided to put together a series of online talks, which we're hoping will kind of meet people's expectations of our technical content. So if you don't know about the Spectrum Scale User Group, we are an independent user group. We work very closely with IBM to develop our events, and we have a number of speakers from IBM who come and talk. We also invite OEMs, VARs and business partners, customers to do talks at our events as well. There is a active email list and Slack community. If you check the spectrumscaleug.org website, you can find out details of how to join in the community. So those of us who run the user group, so there's me. In the US, there's also Christy, Bob, and Bill. And in Australia, we've got Chris as well. So all of the events that we're doing at the moment, we're recording and posting on YouTube, on the Spectrum Scale User Group website as well. So if the time zone doesn't suit you for the live events, hopefully you can go back and review the content afterwards. So we've got a number of other events coming up. It's probably worth pointing out. So IBM next week have a talk on AFM. They're doing that twice on the 16th and 17th. So that's an IBM organised event, but again, it's from the Spectrum Scale development team. And then on the 22nd of September is the next Spectrum Scale User Group talk, which is about functional enhancements in the core of Spectrum Scale. So there's some detail on inode management, vCPUs, and NUMA scaling as well on systems. So our speakers today, we've got three speakers in today. We have John Lewis. So John is a senior technical staff member, and he works in performance engineering within the Spectrum Scale development team. He's been at IBM over 20 years, apparently, and he works with large-scale deployments, has done a lot of work in cloud and containerization of Spectrum Scale, and also network resilience. Then we've got Jürgen from DESI. So Jürgen is a end customer. He's going to be talking about some performance on a new system they've had there. He works in scientific computing there and data management. And our third speaker today is Olaf. And he's been at IBM 15 years, he told me last week. And he sent me a very strange photo of him wearing an IBM spacesuit, although in the end we put a different one on the website. So he's been working as a storage consultant and performance specialist. He works with IBM Research and Development and works on enhancements in Spectrum Scale. So with that, I'll hand over to John in just a moment. I'll remind everyone that there is a Q&A function in WebEx. So if you've got questions as we're going along, please post them in the Q&A. We can stop the speaker, or somebody else on the panel team might be able to answer the question as well. So I'll hand over to John. Thanks.
Okay. Thank you, Simon. Okay. All right. So I'm starting with the standard disclaimer slide. I won't read the whole thing, but now I'm safe with the lawyers. So I'm going to be talking about some performance updates that we delivered in version 5 here, and we hope that this is part of a regular ongoing series of updates. So in terms of the outline, I'm going to start first with some file create performance improvements that went into 503, the base of 503. And then we'll talk about some improvements to MMAP read performance. Those went into 504, PTF in 504. And then we'll talk about a series of changes that went in at various points in the version 5. And those changes are all related to improving file create performance. They have to do with really how creates in a shared directory work. So we'll start with a file create performance improvement that we first really came up as a result of some MD test file create performance work we were doing. So we found that as we scaled up the number of MPI tasks per node, we were seeing file create performance drop off. You can see there's a chart on the right, but the scaling as we added more nodes was degrading as a result of this mutex contention with SGI node map mutex. So the problem was really primarily a code issue. So we put some code changes in to address that mutex contention, basically changed how we're serializing on that mutex. And then I'm including here a couple of other additional changes that help beyond that code change. And I'll talk about those. Those correspond really to the 3 lines on the chart on the right. So there's the MD test. Here we have listed the exact parameter that we were running based on a customer performance issue. In addition to the mutex fix that we put in, the first additional optimization, it was really just to make sure that tuning incorporated max files to cache being set at least as high as the parameter, which is number of files. It's the -n parameter to MD test. So we want to make sure that all the files that MD test creates on any given node can fit in with the file cache on that node. That's the first point. And the second point is to get the absolute best file create performance for workloads that are really doing creates and not creates and deletes concurrently. We want to use another tunable here, which basically reduces the number of inodes that are freshly created, which we keep in a separate list. That allows us potentially, as we delete files, we can reuse them, reuse the inodes, which works very well for workloads that are concurrently creating and deleting files. However, MD test, the way that it works is there's a single phase of file creates, and we're trying to get the best possible create performance in that phase. So to eliminate a separate mutex contention issue, which we are looking at and considering other ways to mitigate, but now for the absolute best file create performance, you'd want to set this max inode dealloc history to 0, which basically disables placing of these inodes in a special list. So just walking through on the right here, we've got same MD test parameters. We're ensuring that all of those files created are fitting within max files to cache. We start with at the bottom line, the blue line is really showing what we got before these changes, right? So you can see by the time we got to 6 tasks per node, performance was really not scaling. We weren't seeing any improvement as we added more tasks. In fact, we're seeing a slight degradation. Now the next line is the red line, which just shows the impact of that fix by itself. You can see we got a nice gain, and these are simply the results that we did or we collected on a machine that was trying to sort of match the customer's configuration. So I can tell you I've seen better numbers than this. I'm just trying to keep the exact same data that we presented back to the customer and that we were working with in the lab. So the red line is showing additional, let's say, gains that come from just the performance mutex fix. And then the third line, the gray line, shows an additional bonus that's obtained by that tuning I referred to that's really applicable to workloads which are doing, let's say, creates by themselves and not concurrent creates and deletes. So we've just set max inode dealloc history equal to 0. That is quite a gain, and I can tell you on other systems I've seen over 100K file creates with that exact same MD test benchmark. So the next set of fixes that I'm going to refer to apply specifically to MMAP read, and I give the APAR number. There is no APAR for the previous fix because it comes in at the base of 503. So when changes come in at the base of a mod level, they may not have an APAR assigned, but generally when fixes come in on a PTF, we can track them with an APAR. And the idea here is that as we have multiple threads which are accessing the same file for an MMAP workload, we have this contention here, serialization that comes from a shared lock, this MML read shared lock. And the reason for that lock is really to ensure that we serialize and correctly handle certain cases in the right path, but it wasn't necessary to have that additional contention in the read case. So really all of that serialization now has been moved to the right flow, and that's the fix that we're referring to here. The change dramatically improves performance when we have multiple threads accessing the same file. So there is some additional work that we're looking at beyond that. I'm going to talk about how we can get the best possible performance until we've done additional changes. But what happens is once we eliminate this lock, and here in the bottom left, I'm just showing a real simple just a picture of what's happening, right? The idea is that multiple threads are accessing the same file, and they serialize on this shared read lock. And what we do now is we basically separate those flows completely. But what's hiding behind that serialization is another lock called the vinfo lock, and that comes into play when prefetching occurs. So I'm going to move to the next slide and show you some additional tuning that we can get when we disable prefetch. Additional performance we can get by setting this mmconfig prefetch aggressiveness read equal to 0. That can be done on the fly. So one recommendation for, let's say, if you're doing a lot of mmap workload and you might have some workloads that do benefit from prefetch, you might potentially even on the fly change that parameter, right? And some customers have done things like in the context of a, let's say, some kind of job script that runs before the actual user job, you could set tunables on the fly without having to restart GPFS. So the first point really is disabling prefetch is giving us the best possible performance. So when you run, let's say, File or something to demonstrate these changes, to see the best possible improvement, you simply run File with multiple threads. Once you have this fix, you're going to get a good solid improvement just by virtue of the fix. To get the best possible performance improvement, you can disable prefetch, just giving us basically like about a 24x improvement in performance. The additional advice that I would give you for mmap workloads in general is to try to avoid remapping the same region, right? And all the real applications that we've seen do follow this rule. But sometimes if you were just trying to represent an application's behavior with, let's say, File or something, this is something to consider. Basically, you want to make sure that you use a large block size for File because the block size is defining the region that gets mmapped. You'd want to map, generally real applications will map a large region of memory, then they perform mmap operations on that region after it's mapped, not keep remapping the same region over and over. So on the right there, we're showing the performance gain. And as I said, this has been validated in the field. Definitely makes a very big improvement for mmap performance. Okay, then on the next set of fixes I'm referring to, were really done in collaboration with one of our Coral customers, Lawrence Livermore. So on, let's say, 4,096 nodes, we started looking back basically at IOR performance. And by the rules of the benchmarks we were performing with that customer, you weren't allowed to pre-create the directories or files that IOR writes to. So what we see here is on a large system, there's actually a considerable performance impact to just creating those files, right? There's a IOR does an open with ocreate call to first create the file before it writes to it. And the more tasks that are writing to a common shared directory, potentially the longer those create operations will take. But there are 3 rounds of fixes that we did in order to get the best possible file create performance. And this actually was quite an important workload for the customer. I mean, in past presentations, I know the team has talked about streaming file create performance, but one of the real important workloads for this customer is simply being able to create a single file per MPI task for the case of a checkpoint. And the latency of that single file is really what matters, not the ability to stream a large quantity of files. It's really each task, one file in a shared directory. And the first round of fixes that we put in to address that use case really had to do with improving how metanode takeover occurs and the rate at which the directory will escape an inode. Because by default, and typically most systems are configured this way, when we create a directory, we'll create that directory in the inode itself, right, in a 4K inode. And then when that directory fills, when the number of entries in that directory exceed the space available, we've got to move it out of the inode. And we'll talk about the process on the next chart. But that change itself had a significant improvement. I mean, the original runs that we were seeing prior to that set of fixes on 4K nodes, we were taking anywhere between 300 and 400 seconds to create for every task to create a file in that shared directory. Once we put this first round of fixes in, we improved performance to between 60 and 160 seconds. A lot of variation in there, but still a considerable improvement beyond where we started. In the next round of fixes, what we did is, upon looking at the actual time that it took to increase the size of the directory as it expands and more files are written to it, we added more flexible controls that allow us to more efficiently expand those directory blocks. And I'll talk in more details about that. But basically, that improved our create case for 4096 files in a shared directory from, let's say, 60 to 160 seconds down to about 15 seconds, which was a very dramatic improvement. And then in the third round of fixes, we added some additional improvements that allow us to establish connections between nodes up front, so that in the process of handling connections on demand, we don't have to take a performance hit or a delay waiting for new connections to be established. That brought us down, it basically cut performance to between 8 and 9 seconds. So I'm going to talk a little bit here just about, and I'm going to go through these kind of quickly here. That'll leave more time for questions if needed. But the general path here of sort of how the directory starts in the inode is depicted. The idea is that we have, some space for the inode attributes. We've got data in inode, and then potentially extended attributes that also can fit within that inode. Once the space, data in inode space for the directory contents are exhausted, we've got to take that directory and expand it out to a sub-block. So by default, we move it to a sub-block. And what happens is there's potential token contention that occurs as the tasks are writing to that directory and determine that the directory now needs to be moved out of the inode to the sub-block. And one of the first things that we can do to kind of improve this flow is to set a config parameter called avoid dir fragments equal to yes. That changes the flow such that we don't move out of the inode to a sub-block, we move to a full directory block. And that, in the case where we know we're going to create a lot of files, is going to avoid basically a stepping stone, this sub-block that we know we're going to overrun anyway. There, I give the configuration option to avoid that directory fragments. That's an important piece of this overall, let's say, strategy. So here I've got a lot of details. I'm not going to dig into them. I'll try to keep it high level and say that there are tokens that we use to control how access to that directory in inode occurs. And basically, as the nodes determine that there's no more space to write to, they need a token which they're going to use to expand that directory out of the inode. And in the case where avoid dir fragments is set, we'll go directly to a sub-block. The issue is that this potential token contention was not, at least prior to the last round of code changes we put in, it wasn't carefully orchestrated and controlled, and there was potential for multiple nodes to make the same token request. So basically what's happening here is nodes, the first node in line that determines that the inode is filling will request tokens, will ask everybody else potentially to revoke other tokens so that they can have the correct access to be able to perform this operation. The problem is that other nodes in the pipeline can also make similar requests, so that there ends up to be a window of time where we have a cycle of nodes that keep requesting for this, let's say, more exclusive token that allows us to move the directory out of inode. What we did to resolve this problem is we added a new flag, the CTM-AXW for data in inode, that allows us to distinguish cases in which this XW token request is made to move a directory out of inode. So once we can see that this specific instance of the XW token is used in this manner, we now can orchestrate the flow of tokens that occurs in the pipeline. This allows us to avoid a lot of unnecessary contention and makes a very large improvement in performance. So the next, let's say, change on top of that is really to allow us to expand these directory blocks more efficiently. And the idea is that typically what happens is we move the directory out of inode to a single block. We had some controls in that allowed us to, let's say, control how efficiently or how many blocks we would split that single directory block to, but we didn't have the ability to control how many directory blocks we initially allocate when the directory moves out of inode. So in the old flow, we just had this, let's say, control that only occurred after the first split. What we did is we added some new code here now that gives us extremely flexible controls over every level of split that occurs on the directory. So each time, even at the very first, let's say, move of the directory out of the inode to, once we said avoid dir fragments, it would normally move to one block, but we can control by setting the nibbles in this configuration parameter how many directory blocks we want to move to immediately when we go out of inode, and then when any more splits occur to those directory blocks themselves, we can control how many splits. Instead of just taking a single block and splitting it into two blocks, we can have a configuration parameter that allows us to define exactly how many blocks we want to split to. So that's this dir pre-split levels parameter. And what I've done here is shown some initial experiments we did that showed us with a scaffolded directory. In other words, when we would create the directory up front before we put all these code changes in, we could see how much time we saved if we created a larger directory up front. And what we found is that there's kind of a sweet spot in the range of around 4 megabytes where we start to see some very, let's say, pronounced improvements. And they're really just avoiding all of this, let's say, directory splitting that occurs recursively, or it keeps occurring over and over as each new directory block fills up. We can define how many blocks we need to split to immediately out of the gate once we escape the inode. And that gives us a very large improvement. So I've got all the details here in terms of how the encoding of the hash tree is done, but basically we look at each nibble of this configuration parameter, and then each nibble defines the number of blocks that we split to, right? So on the very right, let's say rightmost portion of the bit stream, we've got how many directory blocks we're going to expand to immediately coming out of the inode. And there I list the actual values that map back to the hash tree size and the number of directory blocks, and then how much space those directory blocks will take. Key point is, with all those changes, we were down to 15 seconds. I'm trying to show in detail really sort of how that flow occurs, right? How directories go out of the inode, they split to the first level of expansion, then potentially split from there as well. Now, in the third round of changes, the last round of changes, what we found was that, and one of our lead researchers really did the heavy lifting on the trace analysis, but we could see that in the process of acquiring the needed tokens, we were running into cases where we had to make connections between client nodes. And those connections, without being established up front, were costing us time. We did a little bit of analysis on these large systems and found that typically the workload that they're running will define the pattern of connections between client nodes. But you can't really guarantee what that workload will be. And typically we would see that the nodes were not fully connected. So a given workload like this particular job will tend to force those connections more frequently. But if we simply set a configuration parameter that we added for this function, we can do all of that upfront when the daemon is started. We have some parameters we added. These were actually added in 5.10, which allow us to control whether we do all-to-all connections with all the other nodes in the local cluster, a remote cluster that we may join in the case of multi-cluster configuration, or all clusters, local and remote. So with those changes and eliminating that connection establishment, we got our file create times down to between 8 and 9 seconds. So that's a pretty strong gain from 300 to 400 seconds that we started with. And that is what I have.
So John, a quick question. On your round 2, there was a number of those parameters were marked as undocumented. Does that mean that they're usable by customers? Are they going to be documented?
Right now, they are usable by customers. And I think the decision to document that would really come based on requests from the field or requirements from the field. My understanding of documented is not, an undocumented parameter is not necessarily an unsupported parameter is the key point.
I guess the question is how do people know what the right options are for those?
For the one we're looking at right here, avoid dir fragments. The right answer, I think, is it's a trade-off between potential space savings and performance gains. So if you, and this would really, the best way to come to an answer, I think, would be to do some kind of analysis of your workload. But the short answer is, if you have a lot of files that are just expanding out of the inode, or a lot of directories that don't fit within the inode, if your sweet spot was they would fit within a single subblock, then there wouldn't be much value in setting this avoid dir fragments to yes. However, on larger systems or systems where we tend to have a lot more directories with files that won't even fit within a single subblock, then this is going to be probably good performance gain for those kinds of systems. Okay,
thanks. Yeah. So there's a question in the chat. How does this work translate for normal multi-cluster environments with a mixed workload, different storage versus scratch compute storage?
And is that referring to the last change that we're talking about? I'm trying to think of the implications of multi-cluster versus single cluster storage. For this, the last change I referred to here, the obvious change is if you want to use this in a multi-cluster environment, you have to set all-to-all connections either remote or all. Because, so the way things work is when you have a multi-cluster environment, compute nodes join the storage cluster. For all intensive purposes, once they start connecting to that remote storage, they become part of that remote cluster. So the context of connections that they make will be remote connections.
So there's a follow-on question that asks about impact when eviction occurs.
I guess the first thing I always like to start with, in terms of multi-cluster, eviction occurs in the context of the cluster. So for example, a node can join a remote cluster and it can be expelled from that remote cluster or its own local cluster without consequences to the other cluster. In other words, you can join a remote cluster, be evicted from it, and still stay in your local cluster. If you are evicted, your all-to-all connections will be broken in the cluster that you are evicted from. And as soon as you rejoin that cluster, and by default, any node that is expelled from a cluster will try to send a probe to, in the case of a multi-cluster node, short answer is we try to rejoin the cluster. And as soon as we rejoin that cluster, we will follow the rules. So we will try to reestablish all the connections according to this config variable.
Thanks, John. I'm just waiting to see if anyone else, there's a couple more questions. I assume you would also want idle socket timeout equals 0 or something very high in order for the all-to-all connection to be effective.
You know what, that's a very good point. That has been a long-standing recommendation for our large clusters, but it's actually well worth noting that for this really to fit together, that configuration parameter should be set. So once you establish all your connections, they will stay established and not time out.
Some bioinformatics workloads have a client node reading relatively small regions of multiple 50 gig plus files. We've seen this trigger excessive prefetch bandwidth, especially on a 16 megabyte block file system. I think it's a comment rather than a question, I guess.
Well, I can tell you this. We are looking very closely at prefetch, particularly in the case of larger block sizes. So we have a couple of code changes we're working on right now. We got a good test case from a customer that's been kind enough to give us a really good example where you might argue that we're doing more prefetch than we should with a larger block size. So the way I guess one idea, so I mentioned on the MMAP slides that you can disable prefetch on the fly. So that may be an applicable mitigation approach in the interim right now where we work on a more comprehensive set of changes. But I would point out that, I mentioned it before, right? Their schedulers typically have a prologue function. So one thing, customers have done is you could define something like a keyword in your job file, which the scheduler would evaluate and potentially launch a prologue, which sets the configuration parameter, which controls whether prefetch is applicable or not. Some of these workloads, particularly if they're doing things like they might be doing one or two, really they have to be doing at least 2 consecutive reads at a non-zero offset into the file in order for prefetch to kick in. So if they do something like 2 or 3 reads and then they jump to another portion of the file, it may actually be better for now to disable prefetch.
Okay, so I talk about some measurements which we did with an ESS 5000 machine, which has been set up at our DESI environment. We can here see now what the test setup looks like. We had the ESS 5000 with with its 2 head nodes, the NSD-GL20 and NSD-GL21, which are on the top right of the figure. They were connected via 8 EDR links through some complicated InfiniBand fabric to finally 12 nodes on the right side, the SAPO Serve 01 to 12, which were connected with HDR 100 links. So basically we have a one-to-one or ongoing connection with at least EDR speed from the ESS nodes to the test nodes, which we used to run our tests. On the next slide, we can see what we have used. The ESS 5K had 4 enclosures with 92 disks each, with 12 terabytes per drive, as reported by MMLS PDisk. The InfiniBand fabric already mentioned, 8 EDR links on the ESS side, and 12 HDR 100 links on the test node side. And the test nodes were equipped with 1 AMD EPYC with 32 cores each, half a terabyte of RAM, and connected with to the InfiniBand with a Mellanox Connect X6 adapter. On the next slide, we see the measurements done with IOR by Olaf with a 256 gigabyte file size or block size, and transfers in these tests of 16 megabytes, which matches the block size of the file system with random offsets between inter and the files, but inside the files sequential. And there we get a very nice results on the next slide, which is something like 30 gigabyte per second writing and double that for reading. There was a bit more spread in the read values, not too many values were recorded, only 2, so the standard deviation is not very meaningful, but you see we get very nice write and read results. On the next slide, we see some more details from this, but I think we go over to the next slide. This is a different tests done with DD for writing, where we read or write from our 12 nodes. From each node, 4 files with 80 gigabytes per file were written, and I varied the file system parameters. For example, in the first test, we had a 16 megabyte per block size file system with 8 plus 2p RAID code. There we could get a write rate of 30 gigabyte per second. As you can see in the table, the first column, write IB, is the speed as measured as the aggregate of the throughput through the InfiniBand links, while the second column, write FS, is the speed as measured as the sum of file sizes divided by the time the whole test took. Here we see again this 30 gigabyte as Olaf did, but for reading we got slightly slower results, only 44 gigabyte per second. If we now change the file system to have not 8+2 but 8+3 rate code, we get slightly slower write results, but basically the same read results. And if we lower the block size to 8 megabytes, we get only 2/3 of the performance. So we are down to 20 gigabytes writing and 33 reading. And if we go still lower to 4 megabyte, we are at 16 or 15 gigabytes writing and 22 reading. Which is an effect, as Olaf explained, of the number of IOPS which has to be done on disks through the RAID code. Then I did a test where I read and write at the same time. I have 144 threads distributed over the nodes which write and 144 which read files. And interestingly, we get very balanced. Reading and writing both gets, with the 16 megabyte block size file, 17 gigabyte per second on the InfiniBand, and likewise on the file system measurement. And with the 8 megabyte block size, we also get this very balanced measurement with 12 gigabyte per second at the same time. Lastly, we did a measurement where we run GSS perf in a loop from all the 12 nodes with the 16 megabyte block size file system and looked at the NSD throughput from the GUI. Here we see that at the beginning, we are almost at 30 gigabytes per second, but this drops off after something like an hour to 25 gigabytes per second. These measurements are not yet explained, just made, and unfortunately we couldn't do many more measurements because we were mostly busy with setup operations of the systems. And now the systems are in productive use, so we can't do any further measurements so easily without disturbing the users, which we don't want. So these were the results from DAISY.
Yeah, as I said, thank you, Jürgen. So I continue this fourth episode of this talk and give you some more details on improvement in Spectrum Scale in the 5th release. Improvement is for small IO. So my little agenda for the next couple of minutes is a little introduction what we talk about, because as we learned, performance is a really wide range. And I will give you some background information where we came from, helps for better understanding, a new parameter, what else, and a nice example that everyone can recreate this in his own setup. Okay, so let's start here what we're talking about in the next few slides. So let's say it all starts application driven. What the application does, it's not in our hand. It's just it generates IOPS, and there are multiple different IO patterns out there in this market. Read, write, and create, and not just write and create. It's also we have to distinguish whether it is a direct IO or if the IO can be done buffered. We heard some words already in John's talk that obviously there's a huge difference whether it's DIO or buffered in terms of tokens, in terms of whether I'm able to do prefetching or write behind, things like that. And to make it even more complex, I have to compare one IO after the other and distinguish, is this a random IO stream or is it a sequential IO stream? And not just for write or write and create, also same part of the read. So if we're talking about a new next enhancement of the spectrum scale, we need to be more accurate, more specific, and I'm going to talk about performance improvements for small I/O, mostly driven by databases, but there's no need to be a database. It's just small I/O, and I highlight this here a little bit in bold and red. For small I/O, for create or append existing files or create new files, which we appended with sequential direct IOs. It does not mean that it's not helpful also for other scenarios, but this is the intended improvement, and I will show how it really works. So, slide, some background information. The item is not new. If you talk about direct IO versus buffered, you need to have in mind, I mean, surprisingly, some people seems to forget this from time to time, that many storage products or vendors, they're all using cache somehow to accelerate or improve their performance. And it's fair enough. You need to get in mind that all those logics behind doing accelerating things read ahead or prefetching or right behind, they really need buffer to work. So that works in general for buffered IO only. Once an application request comes with an ODirect, or we call it simply direct IO, in general, it means that it tells us to bypass any caches. So that makes it a little bit harder to take those IO and make them somehow efficient. On the other hand, an ODirect is, according to the Linux man page, it's just a high to bypass any caches. There is no strict rule how to handle that. And there are limitations out there. I make one example here for better common understanding. Where you cannot simply direct IO, you cannot simply do the direct IO. Direct means put it somewhere direct, bypassing any caches or buffer. It's simply not possible. And I make one example that we get all on the same page. I put it something like this. So let's make an assumption. You have a file system block already existing and the application just doing direct IO and writes into that existing block. Fine, direct IO, easy to understand, nothing to explain much. So, but at a certain point, this ongoing application fills up this block, and finally, block is full. And the next IO, direct IO, cannot be done direct because there's nothing to write into directly. So you have to step out this IO stream. You have to allocate a new buffer. Allocating new buffer means like John said in his talk as well, we have some impacts regarding token. We need token traffic, we allocate a new buffer, we provide a new buffer, and once the buffer is provided, we can write into. So we flush the dirty data we got from this IO down to disk to follow the expected ODirect semantic. And then we can continue with this direct IO using the direct IO path. But it means we need to change token as well. So just to give you one idea, that's all direct IO, but it needs to be handled separately. And we realized, next slide, even that it is very, very small and very short, is RPCs and stuff for tokens, but it is a little bit time. And depending on the network and the appending rate of your application, it can eat up or adds up to a lot of time. So in other words, you have a lot of additional latency depending on your workload. And maybe, depending on your workload, it's better to stay in this buffer plus sync mode to save that time. And so the basic idea was to introduce that as a parameter. As I said, it's not new. So in the formal release, silently, we introduced a parameter which was called disable DIO. It's a little bit misleading, but it means nothing else but telling GBFS, take those direct IOs and stay in this buffered plus async mode. and do not change any tokens. And by this, you could accelerate certain workloads by some reasonable factors. Show you how it was in the code. So coming from the default old code with no enhancements, give you one example from a very famous database coming with its own benchmark tool. It is called FSPerf. It doesn't matter, it's just a benchmark tool of this database vendor. And if you do a sequential initial write test, as you can see here, the throughput is fairly low, as you can see, 215 megabytes. It tells you nothing because you don't know the environment behind. What I'm trying to show you is if you do the same stuff again on another node with a new code with this disable DIO feature, you see that the same command suddenly generates 1,800 megabytes a second. The customer or the application where we enhanced the code 3 years back was in a so-called in-memory database. So that was really in focus to accelerate the write requests. Nobody was worried or caring about read because in-memory databases, who the fuck is interested in reads? So that's why I show you this picture here. If you do a read, it was still, let's say, not very amused to see 200 megabytes. As we learned in the last couple of years, that customers really start using this disable DIO feature because it was very beneficial also for other workloads, not just for those in-memory databases. You could get a lot of benefits and performance improvements by using it, but on the other side, it was impacting the reads. Therefore, I would say it was only halfway gone. It was not really ready with this enhancement, and this is the way we improved in release 5. Before I come to release 5, I heard there was some rumor that it was not really well documented, disable DIO. So let me do this now. I document now disable DIO. You should not use it anymore with current releases. In other words, if you see yourself exhaust to a workload with small IOs and databases, I think you should look into the direction using the new enhancement, which I showed next slides. Use the new improved release 5, the new parameter. I will explain it. So we introduced a new parameter to enable or switch on this new heuristic, which is called DIO small sequential write batching. By the way, from the name of this parameter, we have a better conclusion or understanding what it really does underneath. I will show you in the next slide. One more comment. First of all, you can set this dynamically within -i. So you can turn it on and off and immediately check your application throughput. And you will see immediately, does it help in your case or not? So no need to do 3 weeks of deep analysis of your IO params. Just give it a try. And if it works, be happy. If not, then set it back. For those who are a little bit familiar with the code enhancement, we still use the Aio Sync Delay. So the code does nothing else but batching together those little tiny small IOs, and it waits for a little period of time. This little period of time in microseconds is the Aio Sync Delay. It's also tunable, but it's set per default once you enable this new parameter to 10 microseconds. 10 microseconds is really a very short slot of time, which in the manner of modern storage, even NVMe is very acceptable. And you see, you will really get a lot of additional bandwidth by enabling it. So, and this time it's from the very beginning, thanks to John, it's already documented in Knowledge Center. So I put the link here that everyone can read it a little bit. And there's the description. I don't read it here. It's for you to be at home. There are 3 asterisks in this second chapter here. When you enable this DIO small sequential write batching, there is more or less, I consider it as a threshold. So the heuristic kicks in when it sees more than 3 tiny small IOs in a row coming in. and not larger than, by default, 64 kilobyte. If it's all true and valid, it kicks in. If not, then it is ignored and handled separately. And you can raise that limit. To make an example, if you have IBM Storage Protect or TSM database on Spectrum scale, and it comes with 256K IOs, it's just give you an example. It's a good idea to try that new parameter, but raise this threshold to from 64 to something higher. It's on one of those next slides. This is not documented in the Knowledge Center yet, but that's why you are here, and that's why it's good that you are here. For those who have now some doubts what we are doing here, I explicitly put one additional chart here from the Linux man pages. All of us which are familiar with application programming, I mean, that's nothing new here. Here's nothing more described than the difference between ODirect and OSync. But to give you a little bit of confidence and make you feel comfortable with the new setting. When an application programmer requests an direct IO or sets the flag ODirect, doesn't mean anything then to try to bypass any caches, and that's described here. There's no guarantee in POSIX that direct IO needs to be saved on persistent storage once it is done. On the other hand, we've seen in the past, in the last 20 years, that usually if an application programmer requests a direct IO, the expectation is that once we act at IO, it needs to be safely on disk. And that's exactly how we still keep to that rule. If we get a direct IO, we acknowledge IO only if it is safely on disk. So we do nothing else but buffer plus an OSync. So you can feel relaxed, your data is safe in GBFS. Once you do direct IO and take the new heuristic and the new enhancement, it's treated with an OSync. So, okay, now I give you a little example that you can play around with this new enhancement without installing a huge database or whatever. It's very simple. You need a tool which is called FIO. I think it's well known and available on each distribution. And you create a simple file where you put in your commands, what you try to test. Important here, I put in the block size and the AIO engine, or the IO engine, which is here AIO. And then you run the command without the enhancement. And no wonder, surprisingly, you get that very low number. Then you do this and then change config. As I said, you can set it immediately, -I, and then do the same FIO again, and no wonder you get surprisingly much better throughput. For those who are thinking more in pictures than in numbers, I prepared this difference here in this little diagram. And for those who are thinking colors, green is the better one. And yeah, that's pretty much it. It's my little summary to give you those two parameters which control the new behavior. DIO small sequential write batching on off, or yes, no. And you have this threshold where you can control the IO size taking into account for that. A little side comment I have for you is it's a client parameter. So it does not really matter what code level is installed on the NSD server side. And in fact, I've been told that there are customers out there running NSD servers with old code. You don't need to worry about that. Even when you run this change config command, you will get some strange error messages like this because of this parameter is not known to this old outdated code levels. You can ignore that. As a matter of fact, the important part is it needs to be installed and effective on the client side, and this needs to be on a recent level. One slide before I put it's now back. I put the release level. It's 504 with the minimum PDF 2, where we introduce this parameter. Yeah, pretty much that's it.
Thanks, Olaf. I'll just see if there's anyone asks any questions on the Q&A. I guess a sort of quick question. So it's obviously cluster based. What if you have kind of mixed workload clusters? How might it affect that?
You can set it on a node base, so you can switch on and off dynamically, and you can adjust it on a group of nodes while all the others doing other workloads. That's possible.
So I'd like to thank everyone for turning up today. Thanks to our speakers, John, Jürgen, and Olaf, for agreeing to speak. Very interesting topics today. Hopefully people have found that kind of out as well. I guess I'll wrap up by just reminding everyone about the next set of events. So there's the AFM deep dive and debugging session, which is being run by IBM Support next week. And then on the 22nd, there's the next Spectrum Scale user group meeting as well. So those are all detailed on the Spectrum Scale user group website. And we'll post the video on there when I get time to put it on there afterwards. So thanks, everyone. I guess we'll wrap up.